Hello and welcome. In the last video, we talked a bit about the history of programming and why it's going to be useful for us to know, especially if we want to do bioinformatics. In this video, we're going to be talking a bit more about the basic elements of programming and what we're going to need to start to be able to speak this language that is so useful for all sorts of things, including bioinformatics. And the first thing I wanted to do was kind of go through a taxonomy of skills and knowledge that we're going to need to be able to solve problems. And at the kind of bottom of this pyramid of knowledge, if you will, is really basic programming elements that we'll go through some of them at least today. And I would call this is kind of in the category of rote knowledge, like you eventually at least will need to just know some of these things by heart. Like it's not going to work to look up every time you need to write a loop, for instance. This is just something that you know it's at some point you're going to have done it so many times that you will remember it. And in order to be kind of fluent in programming, you'll need to be able to write these quickly without having to look them up every time. And you should be able to explain what these are and understand some of these basic structures. And we'll go through them today. So an example question, if we were to test your knowledge on this, would be something like, write an if statement that checks if an input is even or odd, and prints out which one it is. Okay, and then there's kind of a second layer, which is knowing how to connect these things. So if these basic elements like if statements and functions and for loops, if these are like the Lego bricks, then a second level of skill would be knowing how to put some of these things together to build really basic things. If I tell you to build this, write a function that accepts as its input a DNA sequence and outputs the locations of the eco R1 restriction site by using a for loop to check each base position in the sequence. If I tell you like this, use this particular element, use a conditional, use a for loop, you should know how to kind of construct these things. And the higher level then is inductive problem solving. So if the last one, we might call this deductive problem solving, because it's knowing knowing how to execute some instructions basically and do things in proceed in a logical way. But then there's a kind of higher imaginative level where you need to be able to conceive of possible paths to a solution. And this is probably going to be the hardest thing to learn, and it really builds off of these lower levels. So if you can do the deductive part, if you can create simple programs with for loops and if statements when we tell you more or less how to do them, if you also know these basic elements, then you have a hope in solving some more open-ended problems, like, for example, determine which two sequences are the most similar to each other out of the following set. So here, no explicit guidance has been given in how to construct your program or what solution you're going to have to make. It's up to you in this case to figure out, what can I build to solve this, to generate this answer. And so these are kind of the three different levels. And you might have a bioinformatics problem that's going to be quite high level. Do something with sequences, do something, to compare these genes with each other. You'll have to assess the problem, kind of understand it, take it apart, break it down, and identify a good strategy for how you're going to solve it, and then implement that strategy. So at the nuts and bolts level, put together the Lego bricks and test them and debug them and build the program that works. So let's just get started then. So there are a bunch of ways that you can get started programming in Python. One way is to install and run it locally. If you have a computer, a laptop, with any OS, basically you can install Anaconda is a good one. So this is a Python distribution that comes with an editor. It comes with a Python interpreter. It comes with many scientific computing libraries that you might need, and it can be a really fast way to get started. But what I'll show you now is the second option, which is to run Python via the cloud. And Google has a really nice solution, something called Collaboratory. So if you go to this web page here, collab.research.google.com, or if you even go to your Google Drive, which I assume most of you have one of these, and go to New and to More, you'll see this option here for Google Collaboratory. And this will connect to a live server, Google server, and it is an interactive programming environment. So I can make a variable, and we can compute something. That's a plus b, and shift enter here to run this cell. Or you can click the run button, and you can see it's computed an answer. It's a bit slow, but actually the servers themselves are quite fast. The lag here we're experiencing is connection lag. So that's something that doesn't change so much. So we can write some pretty complicated programs, actually, or some pretty demanding programs, I should say. And these servers will be able to run them quite okay. Certainly for our purposes, for learning bioinformatics, is going to be more than okay. And the other thing that's nice about this is you can save these notebooks to your Google Drive. So you can really make it your own. You can add text. So here I can type some text. Wait a minute. Text. I can write a heading, for instance. And it will format it. You can delete cells here this way, and this is this format. It's called an IPython notebook or a Jupyter notebook, and it has an interesting kind of format. So in some situations when you're programming, maybe you would use an editor and then save your program in the editor as some kind of text file, and then run the program externally or separately. In this kind of live programming environment, it's acting as both an editor and a live programming shell, basically. And something to note is that, for example, after I've run this cell, these variables that I've created, they are still in the namespace. So like if I call A here, it remembers even in this other cell that we set A equal to 3 up here. And even if I make another block of code and say move it above this, A is still going to be 3. And it will remember this until we close this notebook, basically. If we disconnect, we have to rerun these cells for it to remember again that we declared this variable as we did. So let's move on. So just some real basics. And I already kind of showed you this with this A and B example, actually. But Python uses variables like most programming languages. And a variable is, we're going to store a number in it or store some information in it. And we're going to use the equal sign to create these variables. And the equal sign in programming is a bit different from how we use it in, for example, algebra. So in algebra, it's a statement of truth saying, A equals 1. In algebra, you could also rearrange, if you have say A on one side and B on the other side, you can subtract B from one side. But in programming, what's happening instead is you're evaluating whatever is on the right of the equal sign, and then assigning it to whatever's on the left. So in this case, the evaluation it's just 1. But we could put 1 plus 1, and what it would do is it would evaluate 1 plus 1, and then take whatever that equals and assign it to A. And because you can assign things, you can also reassign. So for example, I could say down here, A equals 4, 4, yeah. And now A equals 4. So if I try calling A again, it's 4. It's no longer 3. So it's not going to spit out, it's not going to say false, A is not 4, it's 3. You said it was, no, it's going to redefine it. And I can even do something like this, A equals A plus 1. And it's really common to do this, actually, incrementing the value of A by 1. So what it's going to do is it's going to take whatever is stored here in A and add 1 to it. So if A was 4, which it is currently, if we remember, so if we were to run this cell now, it would do 4 plus 1 and assign that to A. So A will become 5 after we run this cell. We run it. Now let's check what A is again. Now it's 5. If we run it again, it's going to go up by 1 again. Now it's 6. So this can be a bit confusing. And there is a shorthand also that gets used to do this. If you do A plus equals 1, this is the exact same thing as this expression up here. So if we do A plus equals 1, it's going to compute A plus 1 and then assign it to A. So we can check the value. Oops, not capital. And now it's 7. If we run this again, now it's 8. So variables can have different data types. So in most programming languages, or pretty much all of them, I guess, you have different data types. And this determines what you can do with that variable. For example, a string is a text, basically. To make a string in Python, you use quotation marks or these apostrophes here, or 3 apostrophes in a row. All of them make strings. They're the same. And we can do addition or arithmetic like we did in the last example on numbers, but we'll get an error if we try to do that with a string. Obviously, it doesn't make sense to try to subtract. We can try it, in fact. I think we will get an error. In fact, you can add, which is why I paused just now. Let's see, let's call something my string. And what happens if we try to subtract? Yeah, okay, so we get an error. So most arithmetic applies to integers and floats, which are other variable types. So a float, short for floating point number, is a fractional number, or a number with a decimal and a certain number of significant digits. And you can use it to represent numbers like 3.6 or 1.9 or negative 15. And integers are countable numbers. So countable numbers like 1, 2, 3, 4, 5, those are integers. And Python is a bit interesting in it doesn't require you to explicitly declare which data type. It tries to figure out what you've made. So like in this case, I didn't explicitly say this is a string, although we can do that. Of course, we still have this error here. Yeah. If we check my string, yeah, it looks like our string hello got saved. But if we also take this away, Python will figure out that we want a string here just from the quotation marks that we've added. Likewise, if we make a variable here, let's call it my number, 3, it will assume that that we mean an integer. And if we can even use the type function here to check what type it got saved as. And it is an int, which is short for integer. If instead we put a period here, and now check the type, now it's interpreting it as a floating point number. Even though 3 point nothing and 3 are the same, even 3.0 here, that's still a float. Notice that we can also do something like, okay, so 1 is an integer, right? But 1 divided by 1, should still be an integer, right? Interestingly, it's a float. So as soon as we try to do some basic math on these things, it will convert them. So, and that's to avoid problems, right? If we try to divide integers, sometimes we'll create fractions, like in this case. And it used to be old versions of Python used to have problems with this. If you tried to divide 1 divided by 3, I believe the answer you would get was 1 or 0. You would get an integer. So this could be very confusing. And I think changes have been made to make that easier. So that's data types. These are the main ones, but there are other data types, and it's possible to make your own as well. This we kind of talked about. So there are two kinds of equal signs in programming. There's the one I just discussed with you, that's definitions, a single equal sign, right? A equals 4. That's one type of equal sign. There's another one, which is the double equal sign. And this is a Boolean evaluation. So this is going to check if this condition is true. So is, in fact, a equal to 4? And we'll get an answer, true or false. Is a equal to 5? False. And it's a bit similar to the less than or greater than sign. So if we try to write a is less than 5, if you remember, we said a equal to 4 up here. So a is indeed less than 5. We get the answer true. We can also do less than or equals like this. Let's do this with 4, right? 4. A is equal to 4, so it should satisfy this, and indeed it does. A is less than or equal to 4. And then, of course, you have also greater than or equal to. And it is still equal to 4. Not greater than 4, though. So we get a false there. And this you've seen a few times, this print statement. So I'll show you this. So if we just want to print out a variable, let's say a, we can do that with the print function. And it's just another function like any other. It takes inputs, and print can take multiple inputs, and it will print multiple things. So here we print a and b, and we can even evaluate things inside it, like a plus b. And it will print all 3 of these things out. Okay, so one of the most important things in programming is the conditional statement. And this is basically, this is a decision. So quite simply, you're asking, is a certain condition true? And if so, do the following. If not, do something else. And it has in Python a particular syntax. It looks like this. And sometimes these are called if statements. And we write something like this: if space, and then we can try this. If a is greater than or equal to 4, and then we put a colon here, enter, and then now we write what it does if this condition is met. So if, in fact, a is greater than or equal to 4, print a is greater than or equal to 4. And notice that this is indented here. And this indentation is part of the Python syntax. So if you don't indent properly, you'll get errors. So this is important. And in the past, the standard indentation for Python was 4 spaces. In this Google Colab environment, 2 spaces is the norm. And I believe if you hit tab, it will just automatically convert that to 2 spaces for you. So that's what happens if a is greater than or equal to 4. If it's not, we can add an else condition like this. We type else, colon, hit enter. Notice we have, again, another indentation here. And now let's say we'll print something else. Print a is not greater than or equal to 4. And that's it. So try running this. And we get a is greater than or equal to 4. And if we remember, we said a was 4. So yeah, that indeed satisfies our first condition here. If we were to change a to, say, 5, okay, and then run this cell again, now we get, greater than or equal to, let's make a less than 4. Let's say a equals 3. Okay, and then we get the second one. A is not greater than or equal to 4. And notice how we didn't specify a condition here for this else case. We just said this is kind of a catch-all. If this first condition is not met, then in any other scenario, do this second case. But what we can do is also explicitly add something, another condition, and that's elif, or short for else if. And then here we have to specify another condition. So maybe we could say, there's a special case if a equals -1 or something like that. Then we print, a is -1. And we can add as many of these as we want. If a equals 0. And always with a colon and indentation underneath, print a is 0. Right, and we can test this out. Like, let's set a equals 0 and rerun this. A is 0. Let's change it to -1. A is -1. So that's how conditional statements work. And a lot of times it's good to visualize programming logic. And there's a convention that's used fairly universally, which is to represent programs with this kind of flow chart. And most of them use the same convention. So if you have a circle, usually this indicates a terminus, just the start and end of your program, or the halting condition if you're Alan Turing. And these parallelograms here indicate inputs or outputs. So, statements like the variable a equals 5, that would be an input here. And, a print statement would print, the result, the sum equals 53, for example. That would be an output. Operations that happen without user input or output, these usually go in boxes. So this is probably the vast majority of steps in your flowchart will be some kind of operation. These will be the most common things probably. And these diamonds here are for decisions. So just like the one we learned, an if statement or conditional statement, this can be a diamond. So depending on what goes in, you get a different result going out. And then we haven't gone through this yet, but loops are extremely important and common in programming. And a loop is just when you go back to an earlier point in the program, revisiting an operation, and oftentimes doing this multiple times will systematically change the value of some state, some variable in your system. Counting numbers, incrementing a number by 1 each time, for example. So here is an example. This is a program that checks if the input is divisible by 3. And this is going to use an arithmetic operator called modulo. And if you don't know about this, this is an operation which just checks the remainder. So if you remember long division, when you divide things that are not evenly divisible, you're left with a remainder, and the modulo operator will check for the value of that remainder. So if two things are cleanly divisible, then the remainder is 0. The modulo will return a 0. So the way this program works is first we start. This is our terminus. We have an input, let's say a equals 10, and we want to know, is 10 divisible by 3? Of course, we know it's not. 9 is divisible by 3, but 10 is going to have a remainder of 1, right? And then this internal operation here, the program will perform. So it'll create a new variable called modulo, and it's going to evaluate it here. It's going to be equal to a modulo 3. And whatever results will get fed into this decision. So if the modulo is in fact 0, remember this double equal sign, if that's true, then go this way, and it will print divisible by 3, and then it's done. If not, if this condition is not satisfied, so if a modulo 3 gives any other number, then we know that it's not divisible by 3, and it will go down this path and will print out as our output here, not divisible by 3, and the program ends. And here you can see Python implementations of this. So here a equals 10, modulo a modulo 3. In the first case, if modulo equals 0, then print divisible by 3. Otherwise, print not divisible by 3. And in this case, we get the answer returned, not divisible by 3 with 10. If we do it with 9, we get the first case, divisible by 3. I can show you this a bit. So modulo operators is interesting. Like, let's try, what was a? A is -1. Let's set a equal to 10 again. If we try a modulo 3, it gives us a 1, right? The remainder is 1. What if we do 11 modulo 3? Remainder is 2. If we do 12 modulo 3, we get 0, right? Because 12 is divisible by 3. So here's just a quick quiz question. Which of the following variables is not a floating point type or float? So think about this for a moment. And if we go through the different options, if you remember, anytime we add a decimal, Python is going to interpret that as a floating point number. So we know right off the bat that a is a float. b is also a float, even though there's no 0 after, there's still a period, so it will interpret that as a float. Down here, 2.0 divided by 3, that is also a float. Remember that if we perform a division, if we try to divide numbers and get a fraction, we'll get a fraction. Python, at least in Google Colab, will interpret that as a float. And then we can also explicitly name things as floats using the float function, which will take whatever we input into it. So 2 here, Python would normally interpret this plain 2 as an integer, but since we've enclosed it in float, it will convert it into a float. And that is the case here as well. So even though we've done 2.4 and then converted it into an integer with the int, we've reconverted it into a float by feeding this as a parameter for the float function. So the only thing that doesn't fit in is this one here, which is in quotation marks. So even though there's a 3.0, which would be a float if we didn't have quotations, anytime we have quotations, it's going to interpret that as a string, and whatever is inside is going to be a string regardless. So the answer here is D. Modules, packages, and libraries. So I mentioned in the last video that there is this huge ecosystem of Python modules, libraries, and packages. And this is one of the greatest things about Python, is that there's just so many tools that are available. And one of these, for example, is the math library. And when you want to use one of these libraries, you just type import and the name of the library or module. And math, for example, has some useful functions like pow, which is power. So if we want to compute 2 to the 8th power, we can use the pow function. And anytime you want to use a function that is called from a library or a module that's not part of the basic Python, then you're going to need to append the name of the library as a suffix with a period in between, dot in between. So here we do math.pow to get the power function from the math library. And you might not know what order to put in. Like, is this 2 to the 8th or is this 8 to the 2? Of course, we can just try it out. So yeah, that's 2 to the 8th there. We could also Google it. Another option is to use help. So you can use the help function in Python. And I believe we could try this with math.pow. Let's see, maybe like that. Oops. Here we go. Yeah. So here I just do help, and it gives us some information. So here's the format: x, y, return x star star y, x to the power of y. So here's just explaining how to use this thing. Another example, factorial. Factorial of x, find x factorial. So we could try that, for instance. What's the factorial of 5? 5 times 4 times 3 times 2. 120. So super useful, and that's just one of many, many, many libraries that are available in the Python ecosystem. And we'll get to explore some more of these. Yes, so since we're using Google Colab, it's good for us to be able to import files. And Google has created their own library for using their interface. And one of the things that that is useful is to be able to upload files. So we can just copy the syntax here. Okay, and then this will give us the option of uploading a file from our computer. So here I would click choose files. Let's see, let's do this image. And now it's literally saving this file to the server. So if we were to, we can go into the file system here and we can see that this image microarray.png has been saved onto an actual computer located somewhere. And this is another extremely useful library that I mentioned earlier as the library that we use for doing a lot of visualization and plotting. And here we have a function. So this library is called matplotlib, and they have a kind of sub module of this library called pyplot, which is just a set of functions that are useful for creating graphs and plots, bar charts and scatter plots and this sort of thing. And they happen to have a function called imread or image read. And here I've just abbreviated it as PLT. This is a common convention because it can be a lot to type this every time, matplotlib.pyplot. imread. So we just shorten it to PLT. And you'll see this is quite common. And here we just call our file. It should be able to find it because we've uploaded it now. And here I'm just going to use this image show. Actually, we maybe don't even need to do this. Let's just try this. Oh, maybe not. Okay. So we need to do im show to display the image. And there we have it. So that's how you upload files. Yeah, and it's nice to know that what it is we have exactly. So if I call this img object, so I created a variable, if you noticed, and I set it equal to whatever this is, imread microarray. So what this is doing is this is a function that takes a file and converts it into a variable. What is that variable exactly? It's a matrix. And if you think about it, any image is just a matrix of pixel values, and we can access a single row of that image, and this is just a set of pixel values, indicating their color and their brightness. So that's the data that's being used. So yeah, here's just a list of useful libraries that are good to know about. So NumPy, we'll go through, is essential for a lot of numerical computation. It's for making arrays, 1D data structures. SciPy, it's used for a lot of statistics and machine learning, has a lot of useful mathematical functions. This is a perfect example of a good library for learning. So you can try implementing a lot of these things first. For instance, I think SciPy has a function for principal component analysis, right? It's a fancy statistical technique, and it's actually very easy to just implement it, right? You just Google, Python principal component analysis, and you'll find some function for doing it, and you basically just try it out. And maybe you don't understand it right away, but oftentimes just playing around with it can be a good way to really understand it. NetworkX is a good one for scientists. It's a library for generating and visualizing networks and graphs. BioPython we'll use a lot as a library for dealing with biological sequence data. Matplotlib I already mentioned for images, plotting, making figures for publications, for making animations. Random, in the last video, I talked about how we can use random numbers to simulate things. And the random library is what we would use for this most of the time. It's functions for generating random numbers and for generating probability distributions and sampling from lists of objects. OS, short for operating system. This is really useful for manipulating files anytime you need to load a file, save a file, write some text, copy and paste, this kind of thing. OS is good for this. Lists. So another data type in Python, and one of the trickier ones, but super critical to understand how it works. Lists are exactly what they sound like. It's just a list of Python objects, and you can create lists of numbers or lists of strings or lists of lists, for example. And the way you do it is, let's say my list. You just use these square brackets here. And this will create a list. And you use commas to separate items in the list. So here we can just make a really simple one. 1, 2, 3. And let's print it out. That's it. But there are all sorts of things you can do with lists, right? This is basically a way to represent data, and a lot of data happens to come in the form of, a list of numbers or a list of items, and being able to go through each item or pick out certain items or rearrange or sort the items. A lot of computing is doing this kind of thing, like dealing with data. And so it's really important to know how to access things. So one tool is indexing, right? So we add these square brackets here and write a number, and it will retrieve the item that's stored in this position that we feed it. Okay, so like, let's change the options. Let's call them, item 1, actually item A, let's call it item B, item C, right? And then if we type my list, square brackets with a 0 in there, that's going to retrieve the 0th element. So in Python, numbering starts from 0. So you have 0, 1, 2. And if we wanted to get, item B here, we put in a 1, the first item with the true first, or the 0th being item 0 here. If we want to get the last item, there's a couple ways we could do it. We could type 2, of course, right? Item 2, 0, 1, 2 here. That's item C. But we can also do a -1. So no matter how long the list is, the last item will always be a -1. If we want to retrieve multiple items, we use colons for that. So if we want to retrieve, say, the first 2 items, we could do this. From 0, retrieve all elements from 0 to up to less than 2. So not including the last thing you put here. So, let's add some more items. Item D. Oops. Item E. And yeah, still just the first 2. If we add a 3 here, then it's going to fetch items 0, 1, and 2. Everything less than 3. And yeah, as you can see, once again, if we do the -1, that's the last item. Suppose we want to get all except for the last item. We could do it like that. We can also reverse the list. 2 colons. Yeah. So now here we're listing E, D, C, B, A. And what you can do is, so this object that's created here is itself a list, right? So I could call this, new list, and new list follows the same rules of indexing. If I want to fetch the 0th item from new list, I do the same thing in brackets and a 0, and here we have item E. And this means that you can skip this first step, in fact. So my list was this one. What we can do is fetch the 0th item of this reverse list that we've created here, and that is still valid, and we could keep doing this, the 0th item of the 0th item. And what it's done now is it started interpreting these items as 1D data structures, strings. So it's fetching the first letter of this item. If it were a number, this would not work. But since strings themselves are kind of like lists, they're a series of characters, we can use indexing rules on them as well. So yeah, we could say like ABC. What's the 0th item there? It's A. How about 0 to 2? A and B. Yeah. So this is lists, and anytime there's something you want to do, for example, it's common to want to append items to lists. So we can do append, and the syntax we would use here is the name of the list. Let's say my list, and then dot append. And we can add another list inside, for example. And it will update the contents of that item. So now we have A, B, C, D, E, and we've added another list here. So there's a lot of different ways you can manipulate these objects. And anytime there's something you feel like you ought to be able to do but don't quite know how, the answer is usually to Google it. Just try to search how to add things to the end of a list, for example. And yeah, and there's another data type, data structure that is extremely similar to the list. But we need to know both of them because they're both useful in their own way. And NumPy is a library that's for making arrays and matrices. And it comes with a lot of numerical operations and things for linear algebra, things like computing the average of a bunch of numbers or computing the standard deviation. So NumPy is really good for this sort of thing. And there are just certain situations where it makes sense to use lists and situations where it makes sense to use NumPy arrays. And they're really quite similar, but they differ in a few areas. So one of these is, okay, well, first let's talk about how they're similar. So import NumPy as NP. This is the convention usually to shorten it to NP. And we can make an array, my array, using the array function, np.array. And it takes as its input actually a list. So we just make a list like in brackets, 1, 2, 3, 4, 5, for instance. And if we check, say, the type of my array, we'll get back this numpy.ndArray, short for n-dimensional array. And that is one of the aspects of NumPy arrays. They can be made multi-dimensional. You can have 2D arrays, basically matrices, or even higher dimensions. And often when we're doing something involving a matrix, for instance, processing an image, which is just a matrix, we'll use NumPy arrays for this. And yeah, like let's try that. We can make a 2D array now. And we do it by making a list within lists. So here I've made in brackets 1, 2, 3, 4, 5, 6, 7, 8, 9. And then this will create a matrix. So each sub list here becomes a row. And let's give it a name, call it matrix. And indexing rules apply here as well. So let's say I wanted to get the 0th element of this matrix. And if you remember, it's going to start at the top of the hierarchy, right? So the 0th element is in fact a list or a row, you can think of it. So item 0 should be 1, 2, 3. We can index on top of that, say we want to get, the 2 in there, the 1th first item. We can do it that way. But NumPy also allows you to use commas for indexing. So if we wanted to get the 0th, similar to like coordinates, like row 0, column 0, we can do that here. And it's this 1 here. What if we wanted to get, let's see, let's just print this out. What if we wanted to get this 6, say? Well, it's row 1, column 2. So we could fetch that this way. Yeah. So it's possible to make multi-dimensional arrays. So like a quick way to make an array full of zeros, for instance, is to use NumPy's zeros function, which takes as its input a tuple, which is basically just in parentheses a pair of 2 numbers, which is the width and height of our matrix. So if we want to make a 10 by 10 matrix, it would look like this. And we can say here the other input to this zeros function is the data type. We can leave it blank, and it will just try to figure it out. Let's say we want it to be 10 by 5, so it should be 10 rows, 5 columns. Yeah, and the convention you can use to remember this is Roman centurion, R and C, rows, columns. So rows usually comes first in indexing, columns come second. We can also make arrays full of 1s, like that. So, quiz question. Consider a list of lists called my list of lists. And it's here in brackets, list 1, 2, 3, 4, 5, 6, 7, 8, 9. What is the proper indexing to return the 5 from the list? So let's consider the options here. So, right, what we want is the item that's stored in here, right? The 5 is here. What we want then is not the first row, the first list here, or row 0, I should say. What we don't want is row 0, we want row 1. And from row 1, we want item 1, right? Not item 0, but item 1. and whatever is stored there, return that. So it happens to be a 5, but these numbers themselves that are stored in the list, that doesn't tell us anything about the position, right? We could have put any number in here. They could all be 9s, for example. So when we say we want to get the 5 from this list, what we're really asking is, what is the position of the 5? And so it should be 1, 1 here. Consider the NumPy array myArray equals np.array 0000001. How can we return a version of this array that is made up only of the first 5 elements, i.e. only the zeros, with the last element omitted? So if we want to omit the last element and include everything else, what we want then is to use a colon. And if you remember, the colon works by taking the first number, where the first position that you're going to start from, and then go up to, but not including the last position. And we use a -1 to indicate the last position. So if we want to omit the last position, we can use this option here, myArray, and then in brackets 0 colon -1. Let's just try that. Zero, 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 1. My array 0, 2, last element. And sure enough, we've got 3, 4, 5. 5 zeros, 5 zeros. And if you remember, well, another way we could do this is, of course, we could figure out what position is the last one. So we have 0, 1, 2, 3, 4, 5. So if we include 5, that would also omit the last position. And they're the same. For loops. So this is another super important concept, or loops, you might even say, is probably the most important thing to know in programming. And it can be a bit tricky to wrap your head around. So I think the best way is to just look at some examples. So let's say we have a list here, just 1, 2, 3, 4, 5, up to 9. And what this block of code here is going to do is it's going to go through each item in this list. And the way it's going to do that is we're going to have a variable here called the iterator or iterable or iterate. And we can call it whatever we want. It's very common convention to call it I. But what this variable does is it takes on the values that are contained in the list that is fed to it. So we use this syntax for creating the for loop for I in a list. And basically, this is a way of saying for each item I that is in this list, do the following. And again, we use the indentation here to indicate that this is happening within the domain of this block of code, similar to how in the conditional statement, we wrote the condition, and then anything that satisfied the condition would be indented. Likewise, with the for loop, anything that's happening within the loop gets indented. And so each time this variable takes on a value in the list, it's going to execute all the things that are indented here. In this case, it's only one line, print I, and the items are just these numbers here, so it's just going to print these numbers out: 1, 2, 3, 4, 5, 6, 7, 8, 9. we could put other items in here and it would print out other things. We could also rename I here to be, J or Q or variable. It doesn't matter. Here's another example. For I in range 0 up to 13, colon. So this is going to do basically the same thing. Here we have a generator, which is just going to, this function will generate numbers, integers from 0 all the way up to, but not including, the number 13. So it will generate numbers 0, 1, 2, 3. Similar to how we made this list here. And in this case, I will take on those values. So the first time through the loop, I will be 0. The second time through the loop, I will be 1. Third time, 2, and so on, up until before 13. And each time it takes on those values, it will execute this line here, print I. So this is very important, so I think we should make some examples. Oops. And so yeah, let's make a list. My list equals, let's say 3, 5, 8, 9. Okay, and we write a loop for, let's say var for variable in my list colon. Let's do something more exotic than just print. Let's compute. Let's say, let's do a sum. Okay, so up here we can say sum equals 0, but each time we go through the loop, we're going to modify the value of sum. So we'll say sum equals sum plus var. So this will be a way to compute the sum of these numbers, and it's going to do it by this variable var taking on the values in the list. And each time it does that, we're also going to re-evaluate this expression here, sum plus var, whatever value is stored in sum. Initially it's 0, and it's going to add whatever value is here, and the first time it's going through, it's going to be 3, because that's the first item in the list. So we'll get 0 plus 3 here, and then that will get assigned to sum. The second time it goes through this loop, var will be 5, sum will be 3, so then we'll get 3 plus 5, and then 8 will get assigned to sum, and so on until the end. And then we can print out the answer. What is the sum? Turns out to be 25. While loops are another type of loop. They work similar to, it's kind of like if we were to combine for loops and conditional statements. Basically, a while loop will continue iterating whatever it's in its block so long as a certain condition holds true. So here, and the language is kind of clear. You can think of this like while this condition is true. So while my counter is less than 10, while that is true, continue to do this, and this being everything that's indented. So every time it goes through, it will first evaluate, okay, is my counter less than 10? If so, and the first time it's 0, right? Then print my counter. Then evaluate this line here. It's going to add 1 to my counter, and then it's done, and it will go back to the top of the loop and do it again. My counter, still less than 10. If this is the second time we're going through the loop, then my counter is just 1, so it's still less than 10. Then proceed. So print it out, increment up again, and so on. It's possible to write never-ending loops using while loops. So this can be a good way to create a kind of error or crash. You could create a condition that's never fulfilled. I could say, while my counter is equal to -1, for instance. And we would see that if we started with 0, that would never be the case. So this would become a never-ending loop. That's not possible with for loops. For loops will end when they reach the end of their input. So yeah, for loops can be visualized using a flowchart. And there's kind of two conventions for doing it. So one takes a bit more work. So here we have a start. We have our iterate I equals 0. And then here's the syntax for the for loop, right? While I is less than 10, from 0 to 10, then do the following. So if this is true, if it's less than 10, then print, say, I times 3. And increment I equals I plus 1. And in for loops, this I equals I plus 1, this incrementation of the iterate is implicit. So here we say for I in range 0 to 10, print I times 3. Here we've we don't have this operation I equals I plus 1. It's included basically in the syntax here. When we decided it was going to be a for loop, we've included incrementation or iteration explicitly. Another way to write this, though, another way to do like a flowchart for this data structure is like this. We just say here, for I equals 0 to 9, do the following. And we could even omit this operation here, this incrementation. So here's test your understanding. After how many iterations will the following piece of code stop? So we have a piece of code, var a equals 16, var b equals 2, while var a is greater than 0, var a equals var a minus var b. And we see that it's this value var a is decreasing by 2 each time, right? It's starting with 16, and then it's subtracting 2, and it's going to do this until we hit 0. So basically that's going to happen 8 times, right? If we start with 16 and we subtract 2 8 times, then we hit 0. So that's our answer here. And let's talk about a real program. And actually, this video has gone on for a long time, so I'll pick this up in the next video. So see you there.